deployed.
Showed a deviation we hadn't seen before.
The start of the Bangkok tragedy the night of May 26, 1991. Don Mueang International Airport in Bangkok was illuminated as usual. On the runway, a Boeing 767-300 with the call sign Lauda Air Flight 004 was preparing for its long journey of over 9,000 kilometers to Vienna. This was the connecting leg after flying from Hong Kong, a journey that, according to the plan, was nothing out of the ordinary. On board were 213 passengers and 10 crew members. Everyone was ready for a peaceful night flight across the Eurasian continent. Captain Thomas Welch, a seasoned pilot with over 11,000 flight hours, along with First Officer Isef Thummer, took off at 11 p.m. in perfect weather conditions. The wind was light, visibility was good, and the sky was clear. The 767 gradually climbed to its cruising altitude, moving away from the lights of the Thai capital and entering the quiet night to the north. According to the plan, they would reach 31,000 feet and fly steadily over Burma, India, and the Middle East before arriving in Europe. What happened in the next few minutes would write one of the most heartbreaking chapters in modern aviation history. There was no prior warning, no word from air traffic control about any risk. Everything was normal until the control panel lit up with the first warning light. It was only a small, seemingly harmless signal, but it initiated a chain of events that went beyond every technical limit the pilots had been trained for. In the tranquil airspace west of Bangkok, the Boeing 767 began to deviate from its course, and none of the 223 people on board could have imagined that they had just entered the final minutes of their fateful flight. The warning signal in the comm sky just 5 minutes after leaving the runway, the amber master caution light illuminated in the cockpit of the Boeing 767. On the ECAM display, the message indicated a fault in the left engine's thrust reverser system. This device is only used once the plane has landed. It helps reduce speed by diverting the airflow forward. However, in midair, this system is strictly forbidden from activating. If it were to deploy spontaneously in the sky, the consequences could be irrecoverable. Captain Welch and First Officer Thummer followed the correct procedure. They opened the emergency checklist and reviewed the steps. The document did not mark this as an emergency situation. The thrust reverser warning had appeared on other flights before. Most of the time, it was just a sensor malfunction. There were no other unusual symptoms. Both engines were operating smoothly, and pressure and temperature were within limits. After a few minutes of discussion, they agreed. Continue the journey. It was an entirely logical decision given the context. No one in the industry could imagine such a warning leading to a catastrophe. Thousands of other flights had encountered similar faults, and none had crashed in the cockpit. The master caution signal was canceled, and silence returned. But in those moments, a faulty circuit might have sent the wrong signal to the engine's hydraulic control valve. A minor glitch, just an incorrectly routed electrical current, was lying in wait, prepared to unleash a sequence of events that no one could stop. The structure and risks of the thrust reverser system in aviation, the thrust reverser, or He Thong Dao Chiu Luke Day, is a seemingly simple mechanism, yet it carries an extremely large risk if it operates at the wrong time. Its purpose is confined to a few brief seconds after the aircraft touches down on the runway. Reversing the direction of the jet thrust forward, helping to decelerate faster, easing the load on the brakes, and ensuring a safe landing on the ground. When the engines are at idle and the flaps are extended, activating the thrust reverser is entirely appropriate. But in the air, things are different. When an aircraft is flying at hundreds of miles per hour, the airflow from the engine must be pushed straight back to maintain lift. If the thrust on one engine accidentally reverses, the sudden change in thrust direction will cause that wing to become unstable. The result is that the entire aircraft can be pulled into a severe roll, lose balance, and enter an uncontrollable situation. For this reason, manufacturers have installed multiple layers of electronic and mechanical safeguards to prevent this system from operating in flight. Sensors, switches, and lock valves are programmed so that the thrust reverser is only permitted to open when the landing gear has touched the ground. But in reality, a small fault, whether a stuck sensor, a short circuit, or a false signal, is enough to make the system misinterpret the situation. And if that happens at low altitude, before the aircraft has stabilized after takeoff, the consequences will arrive faster than any human reaction. This is why a warning about the thrust reverser is never minor. It is a reminder that with just one small malfunction in this complex system, the boundary between a normal flight and a tragedy is only a matter of seconds. Engine thrust reverser deploys in midair at an altitude of approximately 24,000 feet. While the Boeing 767 was flying steadily, the impossible happened. The left thrust reverser, the system only permitted to operate after landing, suddenly opened in midair. In that moment, the left engine reversed its airflow, pushing air forward instead of rearward. The entire aircraft immediately rolled violently to the left, and lift vanished in a matter of seconds. The first officer managed to radio a brief statement. Reversers deployed. That was the quickest way to state that the aircraft was losing control. They tried to cut the fuel, reduce the throttle, performing every maneuver in the emergency handbook. But at a speed of over 400 knots, with one wing being dragged down by the reverse airflow, no system could help the 767 maintain stability. The plane began to fall into a spiral, its speed increasing every second, far exceeding the design limits of the airframe. Air pressure began to tear away at the control surfaces, making regaining control nearly impossible. Radar data showed the rate of descent accelerating rapidly, from 10,000 to 20,000 feet per minute, a number that surpasses all trained emergency scenarios. There was no big explosion, no gradual mechanical failure. It was simply a system meant to ensure a safe landing, reacting at the wrong place and the wrong time. In less than a minute, the entire flight entered an irretrievable condition. The mechanical safeguards, sensors, and review procedures all were defeated by a single electronic fault. And from there, the tragedy began to take shape in the sky. The final battle in the cockpit. In the moments the Boeing 767 was plummeting, everything happened so fast that no one had time to think. The two pilots yanked on the control column, trying to pitch the nose up to break free from the spiraling descent. But at a speed of over 500 miles per hour, the aerodynamic forces acting on the massive airframe far exceeded the stress tolerance that Boeing had designed. The horizontal stabilizer, the part that keeps the aircraft stable, began to shake violently. The enormous wind pressure from the left side, where the engine's thrust reverser had deployed, bent the tail stabilizer. Just a few seconds later, a loud braking sound was recorded in the black box data, and the left tail section broke away from the fuselage. When the rear structure was lost, the entire aircraft became completely unbalanced. All control commands from the cockpit became useless. The 767 spun in the air, large and small pieces of metal flung out as if blown apart. The rate of descent continued to increase, exceeding Mach 1, a speed that no civilian aircraft is permitted to reach. As the airframe became overstressed, the aluminum and composite framework began to break apart. In an instant, the internal forces transformed the aircraft into a massive fireball in the air. The Bangkok control tower radar screen merely showed a single bright spot gradually disappearing. No one had a chance to intervene. A chain of events that started with a small warning, dismissed, misunderstood, and then led to irreversible consequences. That is how a modern, seemingly invincible aircraft can be brought down by a single mechanical fault. The investigation in the shadow of ashes. When Thai rescue teams reached the hilly forest where the Boeing 767 crashed, they found only a scorched area and metal debris scattered across more than a square kilometer. Nothing was intact, except for the small tail section housing the cockpit voice recorder. From the remaining data, experts had only the last few minutes of sound to trace back the tragedy. The investigation was quickly launched, involving multiple parties: the Thai Aviation Authority, Boeing engineers, representatives from the US NTSB, and the Pratt & Whitney Engine Company. Every piece of debris was numbered, and every hydraulic line was inspected. But most were so burned or shattered that it was impossible to determine their exact condition before the crash. The remaining samples were sent to the US, then to Austria for analysis. After months, the report concluded that possibly an electrical malfunction or metallic dust had caused the hydraulic control valve to open at the wrong time, leading the thrust reverser system to spontaneously activate in midair. But the phrase "possibly" appeared in nearly every section of the report. There was no firm evidence, no detail solid enough to confirm the true cause. This was what worried technicians the most. a rare fault, one that could not be reproduced, and no one could say for sure how to prevent it from happening again. In aviation, ambiguity is the most dangerous enemy. And with Lauda Air 004, that mystery remains in the Thai forest, along with the 223 lives that never returned. The fateful 6 seconds and the legacy of safety. Flight data analysis showed that from the moment the thrust reverser system spontaneously deployed until the aircraft entered an unrecoverable state, there were only 6 seconds. 6 seconds, too little time for any human to react correctly in such a complex situation. In that time frame, the entire aerodynamics of the Boeing 767 were turned upside down. Thrust was reversed, the yaw moment increased suddenly, and the altitude dropped faster than 10,000 feet in just a few breaths. No procedure in the handbook could have saved them. When the official conclusion was announced, the aviation world was forced to reconsider. Boeing, along with regulatory agencies and operators, immediately began the process of redesigning the entire safety lock mechanism for the thrust reverser system. A new layer of mechanical protection was added to prevent the reverser from operating while the aircraft was airborne. Electrical circuits, sensors, and feedback signals were also isolated to eliminate the possibility of accidental activation. Lauda Air Flight 004 was not just an accident. It was a severe warning that in aviation, the smallest deviation in design can lead to an unimaginable disaster. From the ashes in the Thai mountains, engineering lessons were rewritten with human lives. And from then on, every aircraft that takes off carries the legacy of those fateful 6 seconds.